All right, today we're going to talk about the graphs of exponential and logarithmic functions. Okay, let's actually just step right into it. Regular coordinate plane, x-axis, y-axis. Let's say y equals 2 to the x. This is just a standard exponential function. And given a value of x, let's say x is 1, y equals 2 to the 1, which is 2. X equals 2, y equals 2 to the 2, which is 4. And by the time you get to 3, 1, 2, 3, 4, we are just off the board, so I'm just going to put a point about here, even though 3, 8 would be the next thing here. So I'm going to just put a few points on this. You could probably find most of these yourself, given the pattern that back here you've got 1/2, 1/4, 1/8, etc. And we would graph it, and it would look something like this. It's a basic exponential function. As it goes up to the right, it goes towards infinity extremely quickly. But as it goes off towards the left, it only gets closer and closer to 0. And that's because whenever we have, back from the rules of exponents slide, we have a to the minus x equals 1 over a to the x. And we know that as this minus x gets closer and closer to minus infinity, 1 over a positive 2, or let's call it 2 right now, 1 over 2 to that growing power is never going to get below 0 because it's a 1 divided by a positive number. So right now it says that it can never equal or get below 0. Because now what is this called whenever we have a part that the graph just cannot cross? It may not be totally visible given the axis that's very thick on the board, but this is called an asymptote, which is a part of the plane that our value can never reach. Like for example, if we were to instead graph a logarithmic function, which we're going to see in just a moment, we have an asymptote going in another direction. Let's go with, instead of y equals 2 to the x, let's have y equals log base 2 of x. So if we remember that log base 2 of 2 to the x equals x. So right now we have log base 2 of 1, 2 to the what is equal to 1. We remember that a to the 0 equals 1 for any a. So let's say that log of 1 with any base is equal to 0. Well, how about log base 2 of 2? That's 2 to the 1, so we'll put an output of 1. Over here, we have if we move over a couple to the right, we've got 4, such that the log base 2 of 4 is 2. And it looks like a line, but the next thing we're going to plot is 8, 3. And as this goes down and down, we see that 1/2 would actually represent 2 to the minus 1, so the log is going to be -1. And it's going to look a lot like the exponential function we did earlier, but instead, it's going to be getting closer and closer to x equals 0 as the y value tends towards minus infinity. And this, of course, can go on into forever, but at a much slower rate than the exponential function increase. And that's because the log function is something like the opposite of the exponential function. So y's log base 2 of x would actually send x to the opposite of its exponent. So when we do this, we can instead run an example and find some integer points. Actually, let's use this as our first example. Let's find some points that we can actually plot. We know that log base 2 of 1 is 0, log base 2 of 2 is 1, Log base 2 of 4 is 2. Log base 2 of 8 is 3. And then back here, as we get to negative powers like that, we've got log base 2 of 1/2 is minus 1, of 1/4 is minus 2, of 1/8 is minus 3. And each time it goes down 1, it gets 1/2 of the way closer to 0. So, in fact, if you were to graph these functions side by side, you're not going to have to be tested on this part, but we also have, so that's y1, y2 equals 2 to the x. If we were going to put this here, we had 2 to the 0 is 1, and put it back at all the points that we had a moment ago. Just go ahead and graph a couple of these. And from here, we again have this nice function. And if you were going to put a line at the y equals x, which I'm sure you remember the graph of this from algebra, geometry, or one of those classes, then you could actually reflect this line down onto that one. And as we go into the homework, we're going to have a couple of things that we want to look for. So, important thing about the log function is that you can never have an input that is less than or equal to 0, because there is no power of x such that 2 to the x is 0. And there is no power of x such that 2 to the x is less than 0. And in the same vein, you can never have an exponent function where the y value is 0, because no matter how negative or positive the exponent gets, 2 raised to that exponent is going to be positive. So, those asymptotes for these clean functions are going to end up right on the coordinate axes. But if you were going to change it up a little bit and instead use a function like, one moment, let me just erase some of this so that we can put a more general function on the board. This next function is just going to be y equals 2 log base 2 of x minus 1. So here we've got, let's plot some points. If x equals 1, then y is going to equal to 0 for log base 2 of x equals 0 times 2 is still 0, but then minus 1 because we have a minus 1 in addition to that term. For 2, we're going to get 2 times log base 2 of 2, which that would be 1, so that is 2 minus 1 is 1. When we get to 4, this part's 2, making it 4, making it 3. And then finally, we're just going to plot a couple more. One's going to live nicely at, hold on a second, at 8, we give you 3, give you 6, we give you 5. And then we're just going to plot a similar looking function to the last one, and it looks like this. And it's pretty much the same, but the growth of it seems to be a little bit more because it's times 2, and it's a little lower because it's got the minus 1. If we instead did y equals 2 to the x minus 1, then we would have something similar to our first one that we did with the exponential, except our function would be at a vertical asymptote, or sorry, a horizontal asymptote. Basically, it never crosses this line instead, because this part never gets below 0. So you'd have the values that we're used to here, here, here and here. But then as we got closer and closer to minus infinity, they'd never get below this line. So they get around here, but never manage to get across that. So the reason that we know that this is the asymptote here, that it can never go past here, is because we know that an exponential term, this is kind of a key part of the video, exponential terms can never get below 0 because there's no power such that this term would be negative or even 0. So the asymptote for a function like that would be, we can never have a y value less than the constant. And for the logarithmic one, we can never have an x value less than an x value that would make this term 0 here or anything less. So this can never have an x value below 0. Or if we instead had 2 times the log of x minus 1, we would never be able to have an x value less than 1. Meaning it would basically just live somewhere around here. It's been a bit of a long-winded video this time around, but I look forward to seeing you in class.